All right, welcome everyone to the International Public Safety Data Institute's December webinar. My name is Alex Fisher and I'm the Customer Success Manager at IPSDI. We're thrilled to have you with us today. For those who might not be familiar with IPSDI, we are a collaboration of fire service organizations built from partnerships we have developed for many years. The IPSDI is a nonprofit research and data science organization, and we host these monthly webinars to provide information to enhance what you do at the local level and give you another opportunity to get insights for decision making at the operational level, the prevention level, or the pre-planning level, all of which depend on good data resources. I want to let you all know that we are recording this session so that we can post it to our website, which I will link in the chat after we get started. During this webinar, you'll be able to use the chat or Q&A function at the bottom of your Zoom screen to ask any questions. With that, it is my pleasure to introduce Dr. Ezekoye. He is a J.T. McGuire Professor of Mechanical Engineering at the University of Texas at Austin. He has served on the UT faculty since 1993 and directs the UT Fire Research Group, which has published extensively on emerging fire and heat transfer topics. Most recently, the UT Fire Research Group has been conducting research on lithium-ion battery hazards. For lithium-ion battery failures, his group characterizes single-cell failures, cell-to-cell propagation, and effects of battery failures on compartment conditions. An objective in these studies is to use experimental results and first principles to develop models at different levels of fidelity and scales to aid in understanding battery failure evolution. Dr. Ezekoye and his group have presented their research findings around the world at engineering and scientific conferences and fire service meetings such as FDIC and the Redmond Safety Symposium. He is a fellow at the American Society of Mechanical Engineers and has received the Society of Fire Protection Engineers D. Peter Lund Award, the NFPA Bigglestone Best Paper Award, and the National Science Foundation Early Career Award. So with that, I'll turn it over and the floor is all yours.
Great, thanks, Alex. Hello, everybody, and thanks for attending this webinar. So as Alex said, I'm going to be talking a little bit about an overview of lithium-ion batteries and the safety issues that are associated with them. We've been very fortunate in our partnerships. Much of this work has been in collaboration with or funded by the organizations shown here. So we're very grateful for that. And I've shown a list of some of my partners, but whether it's graduate students who've gone through the program or other research engineers and participants in our group. So as you know, lithium-ion batteries span a wide range of capacities and uses, and these are everything from wearables and consumer electronics all the way up to energy storage containers. And so what I'm showing here is the range of capacity. So everything here is specified in terms of watt hours, so that's a unit of energy. And it shows that, for example, that a phone might be a 10 watt hour battery system, whereas an EV might be a 100 kilowatt hour system. So the ranges of energy will clearly be important in terms of the hazard that might be posed by any one of these systems if it goes into failure. Now, having said that, I say all the time when talking about these types of systems that these systems are generally incredibly safe, and we're talking about infrequent events. Now, we'll later talk about the frequency because honestly, we don't know what the frequency of failures are with these types of systems, and that's something that's going to be very important to learn in terms of data analysis. So I understand that there are many different areas of expertise on this webinar, and so I apologize in advance if I'm going to say things that you already know. So hopefully I'm going to say something that you know for some part of the audience, and other things that are not as clear for you. And so hopefully we'll touch on all these different issues. So want to talk about a little bit about what a cell is, what a battery is, and what the fundamental components are. And I didn't put my laser pointer on, but here at the top left is sort of the fundamental unit of any kind of electrochemical cell. So it's made up of, and we're going to sort of look at it here, of a cathode material. So this is some sort of metal oxide, an anode material, which is typically some sort of carbon material, a separator, which limits the electrical connection between those. And you can see that actually in this micrograph of this material. And it's all soaked in an electrolyte. And that electrolyte is what allows the charge transfer to occur. So we have this layered structure, which is replicated many, many, many times, and then it's packaged in any number of given formats or configurations. And these could be cylindrical format, and this is an 18650 cell, which is a 2 amp hour, somewhere between 7 and 10 watt hour cell, all the way to this large packaging, which is a prismatic cell, 94 amp hours, about 350 watt hours. So this is a hard case on the left, and soft cases called pouch cells as these intermediate cell configurations. Now, whether it's in an electric vehicle or in a utility scale operation or a laptop, these cells then can be packaged together either in terms of the cell to a module to a pack that can then be eventually put into an electric vehicle. Okay, so we have a basic understanding that there's this electrochemical system that has stored energy that is packaged in many sort of configurations, and these configurations are put together to form the overall energy storage system. And increasingly, as our world becomes more electrified, we're going to have many more of these energy storage systems available. And these can be, again, as a result of our push towards renewables. And so I was just reading an article in the Los Angeles Times about how California is changing regulations in terms of net energy metering. So there's been incentives, for example, given to place solar panels on homes, but what happens is that all those solar panels are dumping electricity into the grid during the sunny, mid-afternoon, afternoon times. And that's not when they're really needed. They're needed in the evening when people turn their air conditioning systems on. So it's been great in terms of incentives to push solar collectors, PV panels because of that. But now there's sort of a move to change the economics in terms of promoting energy storage. So the promotion will be that storage is more important than necessarily just having the renewables in place. So California is an example of a state where policy is going to affect the penetration of energy storage devices like batteries. Now, having said that, I think that there's an awareness that electric vehicles are actually going to be probably the way that we're going to interact with energy storage systems and lithium-ion batteries in a more profound way. And so that penetration is obviously going to affect the fire service, is going to affect a lot of stakeholders, even in terms of the charging infrastructure that's associated with electric vehicles, because of some of the same issues of the cost of electricity during peak times as compared to during less demand times. It may be worthwhile for charging companies that invest in charging infrastructure that make that their business model to invest in large batteries for use in delivering electricity. So the long and short of it is that we're going to all see a lot more batteries. And we're going to sort of, I'm going to focus this really on fire service issues. And again, having said that most batteries and batteries in general are overwhelmingly safe, we have to consider the fact that fires are going to continue to happen, whether or not it has anything to do with a battery. And all this means is that when a fire occurs, there's a high likelihood that a battery will be somewhere in that residence or otherwise that will be affected by that fire. And so the issues become, how does the fire service respond to that and what issues are important? So Really at a high level, then what I want to talk about is failure cases at a variety of scales. What do people see? And this could be an EMS response also in terms of for personal or consumer electronics, discussion of cell failure mechanisms, a little bit of research from our group on ways that we think we'd love to affect battery safety in terms of characterization and what possible mitigation strategies exist, discussion about what data sources exist, and a summary. So batteries fail in a number of ways, and I'm showing everything here from sort of a vaping system where a vaping system could injure someone by failing in their pocket, for example, and lead to a burn, to this is a vaping system also, which caused an ignition in somebody's pant pockets and burnt them, to the Samsung Galaxy Note 7 failure, which was a manufacturing defect and that caused lots of fire hazards and a recall associated with that device. Now, on the bottom left here, and I apologize, I'm going to show a lot of videos just to sort of give a sense of what's going on, is an office with a laptop. And fortunately, there's a video camera that's sort of recording it. And so you see that in a charging process, that laptop fails. And one of the things I'm going to talk about is forensic reconstruction. So imagine that sort of from a failure perspective, somebody's trying to figure out if this is an arson process or if it's a just a natural failure. And so one of the cells was ejected out of the laptop and caused a fire here. So a lot of times when people see multi-point ignition, there's sort of a tendency to assume that that's associated with some sort of an arson event. And of course, in this case, it's not. It's this charging event. We've talked to ATF agents and other fire investigators who've talked about the fact that there are more people trying to cover up arson events by using some battery system, consumer electronics, as a mask for what they're actually trying to do. Increasingly, we're seeing fires again in residential scenarios associated with lithium-ion batteries, and these happen across the world. This was a horrific accident that occurred in an elevator in China where an e-mobility device, a scooter, was being carried in an elevator and it failed during the transporting elevator. So it's a confined space with all these people in there and there's this fire. Closer to home, Fairfield, California, lots of people are using, figuring out ways of making a little bit of money by charging. So you'll see on the left here a garage full of scooters that are being charged. Well, this house on the top right was being used to charge scooters, and there was a failure and a fire that's associated with the battery system during the charging process, and several of these scooters caught on fire. First responders showed up, and some of the police officers also were on scene, and they suffered inhalation injuries because of some of the fumes that were coming off of the battery system, and there was a shelter-in-place order given for the neighborhood surrounding this home. Now, was that shelter-in-place order required? I would say that we don't know yet what the hazard zone might be around these failing batteries. So I think that there's a lot that we need to do from a research perspective to establish the toxicity of these systems and the overall amount of pollutant and toxic plumes that are emitted from them. On the bottom right here is an incident that happened in Montreal where a Hyundai Kona failed within a garage. And what you can see is that during the failure, there was an explosion, and that explosion threw the garage door across the street, and there was again failure and fire in the house. Now, one could say that fortunately no first responders were injured there, but had the first responder showed up before the explosion happened and they'd been standing in front of the door, this could have had really bad consequences. So here's this, these are events that I think unfortunately increasingly we're going to see more of. So these are probably the skills that first responders are going to really sort of interact with these types of systems. Um, Now, having said that, transportation infrastructure is being affected by battery transport. So there's a logistics network that's associated with batteries, whether it's um, before use or end of life, and failures occur there. So in Houston, there was a rail car that was carrying recycled and old batteries to batteries meant to be recycled to a processing center when there was a thermal runaway event in the battery. So they started overheating, and the failure resulted in an explosion in the rail car. Fortunately, it was in a relatively unpopulated area, but windows were cracked and broken up to like half a mile or so away from where this failure occurred. So um, in terms of how we as a research community and the fire service begin to think about what these failures look like, these are sort of ways of thinking about it. We all know that there are challenges in recycling batteries and throwing batteries away. And so we're seeing, again, more occurrences of batteries failing, whether it's in a garbage truck, as you can see in the bottom right there, or in these other transport systems. So here's a recent fire in Independence, Iowa, where you can see that the truck was carrying batteries. Now, there's a question as to whether or not the batteries themselves caused the fire to occur, but you see the strong off-gassing that's occurring, and fortunately, again, there were no injuries, but this is the kind of thing that can happen. In outside of Toronto, a tractor trailer, again carrying batteries, caught on fire and caused damage to the expressway and shut things down. There have been shelter in place warnings in California and hazmat type incident response for other trucks that have carrying batteries that have failed and have caught on fire. In terms of commercial and academic institutions, this can be anything from the warehouse fire in Morris, Illinois, where batteries were contained in a warehouse that the fire service, the fire marshal was unaware that these batteries were there. And as many of you know, there was a long-term evacuation that took place from that community, and concerns about whether or not there had been environmental harm done to the area. To a mall in Beijing. I'll talk a little bit more about this, where there was a fire and explosion that killed firefighters, to this academic building in Australia at Griffith University, where there was an energy storage system that failed and injured a firefighter. Fortunately, not as badly as could have happened. And so again, we'll talk a little bit more about some of these issues. But there's a issue probably in terms of pre-planning that needs to take place in terms of just, and again, an awareness of what hazards exist when the fire service shows up on scene. I think there's more awareness of sort of utility site accidents. So these could be anything from, for us, it was an early sort of awareness of what might happen. This fire outside of Brussels in Drombos, Belgium. And one of the things that always sort of struck me was when you see these fire trucks and the apparatus that close to the incident. This was early, so I would argue that not a lot of people knew what was happening at the time. So there are questions about what the overall toxicity of the emissions from these containerized systems burning might be. Residents downwind of this complained of respiratory irritation and all sorts of other illness and issues afterwards. So again, we don't know what the toxicity is, and that's going to be one of the important things to consider as we move forward. Certainly, we do know that these are explosion hazards, as has been evidenced by the Surprise, Arizona explosion that I'll talk a little bit about, or what occurred in Liverpool, and this Tesla battery fire in Australia. So, what we've said is that across a range of scales, the fire service could be responding um, battery failures, everything from consumer electronics to utility sites, and these are going to require different types of responses and awareness. So many of you already know about the Surprise, Arizona explosion, that it was a containerized 2 MWh energy storage system. Um, the issues are that there are engineered fire protection and explosion protection systems in place, but fundamentally, the reliability of these systems is at this point yet to be completely determined. I'm trying to be positive here, probably. There are a lot of things that we don't know about how these systems actually operate in reality, and so out of caution, the hazmat team that responded waited a couple of hours to make sure things were cool and things that didn't seem like they were moving quickly in terms of the changes within the this purpose-built energy storage system building. But then an explosion occurred, which critically injured firefighters. One was thrown over 70 feet away, an enormous amount of damage. And so this event, I think, has changed our perception in the US in terms of what might happen, and has made us much more aware of the challenges in engineering systems like this and what the fire service response might be. Even after an incident like that, around the world, there are other sort of failures that are occurring. And this, again, is this Beijing, China explosion. 25 megawatt-hour ESS system in a mall failed. And firefighters were, again, doing their job, trying to fight this fire when an explosion happened, and it killed 2 firefighters. This Griffith University fire and explosion. So you can see there was this is part of a green and renewable building that, green energy building that they have on campus. And so there are all sorts of distributed energy resources there. And so there is a battery system up on the top floor there. There was a fire, firefighters responded. And as the firefighters were responding, this explosion took place. It threw a firefighter to the ledge there, could have fallen off. And again, fortunately, he, wasn't injured to the extent that might have occurred. So why do these cells fail? There are a lot of reasons. It could be a manufacturing defect, like the Galaxy Note 7, where the compartment wasn't large enough and there was issues with the separator. So the separator is what keeps the positive and negative electrodes from touching. And so obviously, if that separator is not there, there's an internal short that could occur. And so there are manufacturing issues that could occur. That could be contaminants in the manufacturing process. Typically not the case with what are called tier 1 battery suppliers, but there are a range of manufacturing issues that occur. It could be an abuse scenario. So the abuse scenario could be mechanical damage. So you crash a vehicle. Well, there's you've compromised the cells, and you've compromised the integrity of the internal systems that are keeping the cell from shorting and causing heating internally to occur. Or it could be a system issue. So these electric vehicles are being charged in China, and whether it's the software system, a battery management system that fails or otherwise, then a failure could occur there. So once these sort of small changes and failures occur, there's sort of a snowball effect where the little bit of heating causes subsequent failures, whether it's the melting of the separator between the electrodes that occurs, and there's a heating process in which the heating process overwhelms the amount of heat losses that can be taken out of the system. And this process is called thermal runaway. During this thermal runaway process, then there are all sorts of sort of cascade of issues that might occur in terms of gas generation, fires, et cetera. So lots of research questions that can be posed because of fires, and we've already touched on some of them. How do firefighters know if a fire incident involves lithium-ion batteries? So that's an important issue. And again, whether it's a pre-plan or otherwise, but in general, are there signatures there? What are the hazmat response zones for the incidents? We haven't touched on this yet in our research, but we have a new research project that hopefully will help clarify that. More what we've talked about in our research up until now is what are the heat release rates associated with these fires and what are the explosion risks? And for investigators, how do we know if the battery was the cause or the victim of the fire? Now, there are other things that are going to be important, obviously, for the fire service, like, how do you extinguish these fires? Or what are the electrical hazards, either as you're extinguishing or after extinguishment? So after extinguishment, it's not the case that all the electrical energy has been taken out of a particular battery. And obviously, in terms of, again, incident investigation, what's the toxicity of the post-fire scene? So in terms of what we've done, we've worked hard on understanding gas composition data, which is important for characterizing the explosion hazards of batteries. And so we've published results on the volume of gases produced. So I guess what's notable here is that as these cells fail, you produce a lot of hydrogen, and that hydrogen is obviously an explosion hazard. You produce CO, which is flammable. So these are some of the hazards posed by these cells failing. The rate of release of the failures is important in terms of characterizing the overall heat release rate. So what we've done is we've tested arrays of cells, which might be, again, found in a vehicle, to figure out what the rate of gas production is. And so we can figure out what the rate of gas production is depending on the state of charge. So the state of charge means whether the battery is charged to 100% capacity or some capacity below 100%. This is true, understanding this is important for all sorts of different chemistries. So at larger scales, we've done prismatic cell testing. So this is that 94 amp hour cell that I talked about. This is a package of 14 of those. We can instrument those and test them. And so quick video of that. So the scale here is surprising if you've never seen a battery failure event. So this is an 8-foot tall structure in our research lab, and hardened for, of course, these types of fires. And so there's a cascade of cell-to-cell propagation inside this module. And so what we just saw really was just one cell failing, and this is the burning process that occurs after that. But then there's sort of a cascade that occurs afterwards. Now, why is this a challenge in terms of extinguishment? Well, here is an FAA test with a fire-resistant container, and there was a suppression system. So there were a bunch of these 18650 cells in this compartment, and the cells failed. There was ignition and a fire. The fire was extinguished by an aerosol fire suppression system, but that doesn't cause the cells to stop failing. So the internal failures in the heating in the cells propagate from cell to cell and continue to generate these flammable gases until there's an explosion. So there are challenges in extinguishment, and a lot of very good research organizations have been studying these extinguishment processes. As I mentioned before, lots of different gases are produced by these failing cells. This is that 94 amp hour, that block-shaped prismatic cell that I showed earlier. And what we can do is we can figure out, for example, how much gas is produced and the composition of the gas. And that is important to then think about what the overall explosion hazard might be for that. So that little book-shaped brick of gas, well, right there that I'm showing up here, it produces 225 liters of gas. I mean, and this is flammable, toxic gas. So not surprisingly, then there's an explosion risk associated with that. So we, for example, characterize what happens to a module, a whole block of these, in terms of the propagation rate and the mass that's generated. And so you see this, again, there's sort of a increasing, because of the heat transfer between the cells, there's a increased rate of which mass is lost or in which the cells are failing. And so this is sort of an acceleration in the heat release rate. And once this module fails, it will influence the adjacent module, which will then influence what might be occurring within a room, for example. We've done testing of cells within a compartment like a closet, because what happens if somebody has a small energy storage system in the closet, and not surprisingly, there are explosion risks associated with that. So what you saw there is there's initial gas release. It's a flammable gas. The heating then occurs because the cell and the gases coming out are igniting this flammable mixture, which then causes this overpressurization or explosion in the closet compartment. Really quickly, I'll talk about what we've done in terms of fire forensics. So when you think about after a fire has happened, was it the battery that caused it, or was it the victim of it? And so one of the things we figured out, and this is not, that um, it's sort of expected, but we have to document it, is that the more energetic the cell is, the more likely it is to ignite materials, for example, underneath it. So here's sort of a mock-up of a upholstered system underneath batteries that were failed. These batteries are everything from fully charged to 30% state of charge. And so, not surprisingly, the low capacity cell is unable to ignite this upholstered furniture system, whereas 100% capacity, it's very easily able to. So the question becomes, for an investigator, is there a way after the fact to determine? So you've got failed cells in all these scenarios. How would you know what the state of charge was after the fact? So one of the things we figured out is that the amount of mass that's lost is representative of the state of charge prior to failure. And now we're also looking at chemical characterization of the components of the residues, if you will, of the cells. And we've shown that there's a correspondence between the nickel to manganese ratio, cobalt to manganese ratio, and the state of charge at failure. So we think that this is going to be a path forward for understanding this. Another thing that we've done is we've developed a instrumentation system where we can instrument a cell with a micro heater inside of it and temperature measurements. So we can then put this cell, this instrumented cell, into laptops or other devices to see how they fail and to see what the cascade of failure might be. So this tells us, for example, what's the likelihood that if a laptop failed, it would ignite, for example, a sofa or some other package remote to that primary failure. So we record things like the heat fluxes and temperatures around it and understand that failure propagation. Some of our new projects are a project with NFPA that's funded by the Department of Energy. It's Empowered. It's a firefighter training system. So we're working with Austin Fire Department and other local departments to do some acquired structure testing where distributed energy resources like an EV and residential battery energy storage systems are going to be compromised. And we'll look at the failure propagation there. And a relatively new project, again, is a DHS FEMA sponsored project that's going to look at toxicity characterization of lithium-ion cells during failure. And we're already sort of preliminary data suggested there are all sorts of volatile organic compounds that we can speciate at very, very fast times relative to failures. So typically when people look at speciation, it's after the fact, but here we could speciate in situ as the failure is occurring and find out when does the hydrogen come out, when does ethanol come out, when are all these different components coming out. And we think that this is going to be extremely important in helping develop the next generation of firefighter gas sensor systems to understand better whether or not there are signatures associated with lithium-ion batteries. The last couple of slides, I'm just going to talk about data. So we're trying to compile a database of battery incidents, everything from consumer electronics, e-cigarettes, all the way to utility scale. And so it's in its infancy as far as the database is concerned, but it's searchable. It's available at our website, utfireresearch.com, under tools. And so the searchable index is available. We need help in terms of populating it more. There's a lot that's going on, and we'd like to understand better frequencies and types of batteries. I mean, obviously, U.S. Consumer Product Safety Commission is another source, and we are leveraging information from that source also in terms of understanding better what's going on in our incident database. Another database service or tool is the Electric Power Research Institute, EPRI's database, which focuses on utility scale energy storage incidents. And it's a great database. Again, it tells us, for example, explosions versus fires in that database. So at a high level, in terms of a summary, lithium-ion battery systems are generally safe. We don't know what the frequency is. We think it's important to understand the frequency. We think it's important to understand if there are particular types of cells or particular types of systems that are failing more. That way, effort can be put to improve those. And the research that we and many others around the world are doing is helping to uncover how these cell failures occur, so that mitigation steps can be developed at all sorts of different levels, whether it's at the compartment scale, whether it's at the module scale, or for people who are sort of working at the cell scale to develop these mitigation strategies. I encourage you to reach out and help us in terms of getting better sense of what is going on in your jurisdictions and in your communities as far as battery system failures. And so I have a link there showing where you can contact us and provide information as necessary. Thanks for your attention, and I'm happy to answer questions.
Thanks so much. All right, we did have a question in the chat from William. I am going to see if he's still there and turn on his mic in case he has one and would like to give any clarification. But he asked, regarding the engineered fire systems, are you referring just to the ones in this situation, which was the Surprise, Arizona case study, or engineered fire systems in general and use for these applications?
Yeah, I think that we would say that the engineered fire systems that were in place for Surprise did not they did not work in the sense of mitigating the explosion. And perhaps the issue was that there was not an awareness of the explosion hazard that could have occurred. So maybe the engineered fire systems were great for the fire, so there was no fire, but there was obviously an explosion, and that was not foreseen. And so that was an issue. So maybe I should clarify, it's engineered fire and explosion systems as compared to just focusing on the fire. And I think it's the complexity of these systems in terms of the logic that has to occur in terms of the sensor systems and the mitigation steps. So, one of the mitigation steps for the explosion hazard is at FPA 69 is to sort of contain or minimize the flammability of the compartment, and that could be done, for example, through a ventilation step. Well, from a ventilation perspective, you think, well, I don't want to ventilate a fire, so the logic and controls to say, is it a fire hazard or is it an explosion system, and how do you go sort of between the explosion hazard and the fire hazard as these cells are failing is I think it's in its infancy in terms of how we deal with it, and different organizations, companies, solutions are being developed on this. But again, it's sort of evolving, and there's perhaps a fundamental level of work that has to be done on understanding how the systems fail first before we can sort of get really robust solutions in terms of these engineered systems. I hope that helps a little bit.
Yes, thank you.
Mm-hmm.
Great. We also had a question in the Q&A from Jesse. With the amount of mass loss indicating SOC, how does a flashover event impact that?
That's a really good question. And so we think it's, so we've done burns where we've failed individual cells at different SOCs. It's not under a flashover environment, but sort of supported over a pool fire. So this is sort of this idea of cause or victim of the fire. And here's my take on it. It doesn't change much. And the reason it doesn't change much is because the violent ejection that takes place as the thermal runaway process is taking place, that's the thing that primarily drives the mass loss. Sort of the drying out of the electrolyte during a flashover event. So you have a high heat flux and you say, well, I should be drying it out. That's a much harder process to take place. So even just trying to dry out for our own research purposes, electrolyte is very difficult because, this is a capillary driven process. And so you've got these small voids and relatively small volumes, and the capillarity is really strong. So, under very high temperatures for very long times, it's still very difficult to dry out these systems. And even then, I'm not ejecting all the particles and all the other material that is part of that mass loss. So the mass loss is really more strongly driven by the thermal runaway process and that violent ejection as compared to sort of long-term heating after runaways occurred. So sort of a simple test that we've actually done then is we've taken a very, very low SOC, like we discharge a battery, cycle it to 0 and heat it up, just really heat it up. And it's really hard to drive out any material from it and change a mass in a meaningful way. So that's a great question. Thank you.
Great. We have another one in the chat from David. He said, what kind of sounds might be heard just prior to a battery explosion? This might be helpful in gathering information from possible witnesses.
Oh, that's a great question. It depends on the type of cell. So the cell format matters because some types of cells are vented. So the cylindrical format, the hard casing cells, whether it's cylindrical or prismatic, they have vents on them. And so the vent popping is something that somebody will absolutely know and notice. The pouch cells, it's a laminated, sealed, aluminized polymeric system, and it just sort of opens up. Now there will be a whoosh, and that you'd hear, but it's not as dramatic a sound as the prismatics going off. And I think you heard it in our video. I'm happy to play it again. We've tried to reconcile. Let me just go back here. We try to reconcile and identify when cells fail here. So when you see on the left here, event, one of the best ways to identify that event is actually acoustical. Okay, so the acoustic signature of that venting is, I would say, more useful than sort of visual or even sort of any kind of gas measurement. So so understanding when it fails by sound is a really important component to it, but it all depends on the type of cell it is. And I don't know if, from a forensics perspective, I don't know if asking, certainly more data is better. Did you hear anything? I think that is absolutely useful because it says, hey, did the battery go off or didn't it go off? And depending on what they say, can be used to understand better what events occurred. So yeah, I think it is worth asking. It's just, I guess, again, depending on the type of cell it is. Great point.
All right, thank you. That's all that we've received thus far. So I'm just going to give a last call for questions and just remind everybody that we did add the IPSCI website training page to the chat. So if you want to send that around, we'll have the recording of this seminar and all of our previous webinars on there for you to share with others. I did also find the UT Fire Research that apps incident link too. So I put that right in the chat as well for anybody who would like to go there and submit any information or just look around as well. All right, well, I do not see any other questions coming through. So with that, I will say thank you everybody so much for attending. And thank you so much, Dr. Ezekoye, for coming and presenting this talk with us today. Like I said, we'll be posting this recording to our website in the training section, so feel free to use it as a reference or share it with others. So have a great day, everyone. We hope to see you at our next webinar. It will be January 20th, and it will be related to wildland-urban interface and fires happening there. So thanks again, everyone. Have a wonderful day.
Thanks, everybody. Thanks, Alex. Take care.